Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 47. So we were discussing about the intensities of the spectral lines, and in the last quite a few lectures, and in this lecture also we shall be concerned with the shapes of spectral lines. So the shapes of spectral lines. Now you may be wondering, this line, this sentence itself, might not make much sense. I've already told you that it's a spectral line, right? It's a spectral line. So what do you mean by, like a shape of a spectral line? It's already a line, right? Line is already a shape. So what do I mean by the shape of something which is already a line? Okay, right? And of course, the big question, why care about this in the context of astrochemistry? All right. So these are the two questions we shall be addressing, followed by actually talking about the shapes of the spectral lines themselves. Now notice that, all along, if you recall, when did we start discussing about spectral lines in this lecture? Whenever we started our discussion on detecting atoms and molecules in space, right? That went back all the way to our discussion of the Fraunhofer lines, right? Line, always. It was always a line. It was always a well-defined, discrete line, right? So we get this impression, we get this impression that upon absorption and by emission, right, we get a well-defined, right, well-defined, sharp and discrete line, right? This is what I've been telling you all along in this course, right? Corresponding to any transition in a molecule. It can be an electronic transition, a vibrational or a rotational transition. We shall be getting a well-defined, sharp and discrete line. And these lines are what are going to be helpful for characterizing the bound system that is present in space, correct? Okay, now it so happens that in reality, right, when you actually measure a spectrum, either in the lab or, like you obtain a spectrum from molecules in space, right, you notice that it is not actually a line, right? In other words, when I speak of a line, I'll be thinking of one sharp line such as this. But notice that even when I draw this, right, the line is going to have some width. In other words, the line has some width. This is a line with much smaller width. And this is a line with some larger width. So the spectral line that I'm talking about, right, it has some finite width, and this width is also of consequence, as we shall see how, and that is what is meant by the shape of a line. So when I talk about a shape of a spectral line, I'm talking about its finite width, right? Now why should it matter? It should matter. I'll just give you a hypothetical example. Let us say that, two molecules or two atoms have the spectral lines very close to each other, right? When they are very close to each other, and let's say you have and experimentally you record the spectrum and you see that the lines are very close. How do you even know whether they are two different lines or one line having a specific width, correct? if there were very sharp lines with zero width, okay, right, with zero width, then you know that, okay, there are indeed two lines and two different molecules. But if one line itself has a finite width, you will not be able to differentiate the molecules, right? So therefore, understanding this shape, in other words, the finite width, okay, right, the finite width of a spectral line is critical to accurately detect molecules in space, okay? So remember that our task is not just to detect molecules, but also to accurately detect what is what, correct? Okay, we should be able to distinguish between, for example, various isomers and between molecule A and molecule B. It is not sufficient if we tell that there are molecules in space. We must tell, oh, this is the specific molecule that is present in space, all right? And for all this, understanding the notion of line width is important. But what I have not told you is, what are the factors which cause the line width? Okay. Why should there be a width, as part of a spectral line, as part of a why should a spectral line even have width? Okay, well, it turns out that there are three reasons for it. Okay, the first reason is based on quantum mechanics, which are written as QM, and it is called as the natural width. Okay, I'll explain each of these very soon. Okay, right? So first is due to quantum mechanics. The other is due to increased pressure. Okay, right? So the idea of the concept of increased pressure will also lead to some width to a spectral line. The third one is what is called as the Doppler broadening. Okay, right? So the Doppler broadening of a line is also going to give it some width. Okay, right? So we shall now be discussing each of these factors in this lecture, hopefully only in this lecture, or if we cannot finish, also in the next lecture. All right? And I'll talk about the natural width of a spectral line. Okay, this is point number one. So the natural width of a spectral line, which arises as a result of quantum mechanics. Okay. Now, what do I mean by this? Why should this arise, and why is it important? Okay. All right. Now, once again, go back to a few earlier classes. Let's have a small flashback. And I was discussing with you about the properties of waves and particles, right? We were discussing the idea of light interaction with matter, right? And as part of it, we were discussing what wave is and what a particle is. Okay. Now, as a consequence of this wave particle nature of both light and matter, as a result of the wave particle dual nature of both light and matter, okay, right? We have this phenomenon, okay, we have this idea in quantum mechanics called as the Heisenberg's uncertainty principle, which is called as HUP. I mean, I'm just shortening it as HUP, okay, right? You must have, of course, been, studying about this Heisenberg's uncertainty principle right from high school. But, there is a specific variation of this which is used in the context of the spectral line width. Okay, we'll talk about that now. What does the Heisenberg uncertainty principle say? I don't care about the mathematic formulation for our purpose. What we are going to be worrying about is rather about the understanding of the principle, right? Such that the wave particle nature is what is responsible for it overall, okay? And how that leads to a width to a spectral line. This is going to be page 4. Now, see what characterizes, a particle. A particle, I'll just write it here, okay, right? Now, a particle, we looked at various differences between waves and particles, right? Now a particle is in general localized, right? So a particle is localized and the wave is delocalized. I would exhort you to, like go back to that lecture, approximately, some 15 or 10 or 15 lectures earlier. And we looked at various properties such as mass transfer, energy transfer, and then the definition of a well-defined number of waves versus well-defined number of particles, right? And all those, the one of them exhibiting interference waves and the particles not exhibiting interference, etc., etc. The crux of the issue is that a particle is localized. I can pinpoint and tell where the particle is, right? Whereas at any given instant. Whereas for a wave, because it's a wave, right, it moves very fast. So wave is delocalized. Okay, right? Now, so as a consequence of this wave-particle duality, which is a paradoxical situation, right, we get this expression, which you must be familiar with in high school. That is, delta px times delta x is greater than or equal to h bar by 2. This is the Heisenberg uncertainty principle. This is the mathematical statement given where, this term is the uncertainty in momentum and this is the uncertainty in position. Okay, right? Now notice that the quantum mechanical entity could be moving along all three directions. Okay, right? It could be moving along any directions such that there is a component from the x, y, and z, all parts. However, the uncertainty principle holds good only along the same direction, right? Okay, so we are only considering the uncertainty along the momentum, the uncertainty of the momentum along the x direction, right? If we consider the position's uncertainty along the x direction, okay, so this should be x and x. That's the important point. Okay, that is something they perhaps don't tell you at high school, but one could easily derive this expression as part of a routine quantum mechanics course. Okay, so this is the expression given. What is its meaning? Its meaning effectively translates as, if you are able to localize a particle, right? If you're able to localize a particle, then you never know, you let's say you're able to localize the particle. In other words, your delta x is going to be very small. Okay, right? If your delta x is going to be very small, then your delta px has to be very large. Okay, right? And likewise, if you're going to be, let's say that you understand, you fix its momentum, right? Which is a property of a particle. Okay, right? You fix its momentum, the uncertainty in momentum is going to be very less. Then therefore, because the value of h bar is very small, there is going to be a lot of uncertainty in your position. Okay, that is, so this mathematical statement translates qualitatively into this idea that it is impossible to simultaneously describe some entity accurately, right, such that it is both localized and delocalized at the same time. Okay, right? Now this is the expression in terms of momentum and position. There is an equivalent version, which is or delta E, right, and delta tau, which is greater than or equal to h bar by 2. Now this is the expression, right, we shall be using for spectroscopy. I'll explain each of the term here. Okay, so delta E and delta tau is greater than or equal to h bar by 2. Here delta E is the uncertainty. See, the phrase uncertainty itself, right, is also mathematically well defined. We're not concerned with it in this course, okay, yet, okay, but one can actually precisely define it, by using standard deviations and all those quantities. But we're not going to go there. But I'm just going to tell you, for the sake of increased depth of knowledge, that the phrase uncertainty is mathematically well defined. Okay, that's it. So delta is the uncertainty in the, let's say, the energy of the molecule at any instant, and your delta tau, right, is going to be the uncertainty in the lifetime of the excited state. In fact, even this term and delta E, right? It could be more precisely also understood as the uncertainty in the energy gap between the levels where the transition is happening. So this is going to be the uncertainty in energy gap, right? For the molecule, right? We're basically talking about the energy gap between an excited state and a ground state, okay, right? So this is the uncertainty in the energy gap, and this is the uncertainty in the lifetime of the excited state, okay, right? So now what this tells us is that if I'm able to accurately get the energy at any instant, right? I shall not be able to get the lifetime pretty accurately because h bar is very small again, right? And vice versa also. If I know the lifetime, the energy of the transition, I cannot get it accurately. Okay, so this is a natural consequence of the wave-particle duality. All right. Now, in fact, you may be wondering at this stage, okay, the E, I can get by somehow my E equals h nu, I can get a magnitude of delta E. How do I even get this delta tau? That is the lifetime of an excited state tau. How do I get this tau of the time? How do I get this expression? From where do I get an expression for this t? Now this is where our discourse on the Einstein coefficients was helpful. If you consider our discussion of the Einstein coefficients, and if you consider the spontaneous emission term, right? For the spontaneous emission term, I'm using the same notation, right? But 2 refers to the excited state, right? And n refers to the number of electrons. So that is given by the number, which is the number of electrons in the excited state times B21, if I'm correct, right? That is given, this is the Einstein coefficient, correct? Okay. Now, what is the unit of this Einstein coefficient? If you think about it, this is going to be some number per time, right? This is some number per time. This is some number. So therefore, this B21 is going to be some time inverse, right? Because this is per time, right? So the lifetime of a complex, okay, right? Or the lifetime of any excited state, the lifetime of a molecule could be defined as, it's not a unique definition, but one that is useful for us, okay, right? So your tau can be understood as the inverse of the Einstein spontaneous emission coefficient, and this is now units of time, okay, right? So the delta E, you can measure using various formulae, right? And also from the spectrum itself. And tau, one way to get it is as the reciprocal of your Einstein spontaneous emission coefficient, okay, right? So this is how you get delta tau, all right? So now we understand that due to the intrinsic wave-particle dual nature, which is what is the quantum mechanical manifestation, right? Due to that effect, we have an intrinsic problem. We cannot get delta E precisely. We cannot get E or tau precisely. Okay, right? And both of these are important for us to get a line without any width. Okay. Now, due to the finite nature of this, due to the idea that both of them cannot be simultaneously precisely obtained, right? We're going to be having a width to a line. Okay, and this is what is called as the natural width. The natural width. Now, starting with this expression, that is your delta E times delta tau is greater than or equal to h bar by 2, it can be shown, okay, right? It can be shown that the difference in the frequency, for example, see, we use the expression E equals h nu, right? That is like we use one value of a frequency to get the spectral line, okay? However, there is going to be some error in the magnitude of the frequency itself, okay, right? So it could be measured in terms of frequency or wavelength or wave number also, okay, right? Now, in terms of wave number, which is a reciprocal of a wavelength, right? Starting from the Heisenberg uncertainty principle, okay, the exact derivation, is reasonably easy. We could perhaps do it in a tutorial, right? Now, the magnitude of this, the error in the exact wavelength or wave number or frequency is given by 5.3 by tau centimeter inverse per picoseconds. Okay. Now, note, this is starting from hub. The expression is given over here in this page. Okay, right? You start with this expression, and based on this, right, noting that your tau is nothing but the reciprocal of your Einstein's spontaneous emission coefficient, right? Then you get the spread, okay, right? The spread in the wave number, right? Of course, one can also get the spread in the frequency, wavelengths, etc. But this is a convenient representation, getting it in terms of wave number, right? This is given by this formula, 5.3 by tau centimeter inverse per picosecond. Now, this is wave number, which is a reciprocal of the wavelength. So therefore, I get the centimeter inverse. And picosecond is because I have the tau, which is the lifetime of an excited state complex, excited state, that is given by, some time unit. It so happens to be picoseconds here. Are we good? Okay, right? So this derivation, we shall be seeing in the tutorials. So in the tutorials, we shall be deriving the expression for the change in the frequency. All right. Okay. So we understand that the quantum mechanical nature, that is the paradoxical wave particle nature of both matter and light, that itself adds to a natural width to the spectral line. Okay. In fact, it can also be said that your transitions, right? Your transitions can be of different types. Okay, right? It can be electronic transitions. That is a change from one electronic state to another, or a vibrational transition, or a rotational transition, etc., etc. Now, for example, if you consider an electronic transition, for example, if you consider an electronic transition, which occurs on the order of, let's say, approximately 10,000 picoseconds, right? If the recall, I told a few lectures ago that these transitions happen of the order of picoseconds, right? So let's say that the electronic transition happens at, say, around 10,000 picoseconds. In that case, the line width, okay, right? Your overall line width, or this quantity right here, okay, right? Your delta nu is going to be roughly around, how many zeros will be there? 0.00053 centimeter inverse, right? Centimeter inverse. Are we clear, right? You just use the same formula, this divided by 10,000, right? Okay. So for an electronic transition, you can say that this is negligibly small, but we never know, right? What if there are two molecules which show lines which are like closer than this number, which are like smaller than this number, right? In that case, we have to resolve the lines even better. So this natural width, right, arises due to quantum mechanics, and it is of, let's say, 5.3 to 10 to the power centimeter inverse magnitude. All right, when the transition time is 10,000 picoseconds. But let's say that, for the rotational lifetime, okay, right? Now, this number, in fact, I can now ask you a question. Between electronic transition and rotational, vibrational, rotational, etc., do you think, this natural width, is it likely to be smaller or be bigger as we go from electronic to rotation? The answer is, it's going to be smaller and smaller, okay, right? For vibrational, rotational transitions, etc., okay, right? Delta nu is smaller than that for electronic transitions. Now, why is that? Well, that is because the time taken for electronic transitions is going to be much higher, right? Because two electronic states are much higher in energy than, when you compare between, let's say, two vibrational states or rotational states. We looked into the separation of states, right? I mean, quite a few lectures earlier, right? So that is all useful in understanding this idea that the natural width is going to be optimally seen in electronic spectroscopy, right? Whereas with vibrational and rotational spectroscopy, etc., the magnitude is going to be much smaller. Okay, right? So how smaller? In fact, so small that the most optimally resolved spectrum, okay, right? The most optimally resolved rotational spectrum, has a width of delta nu. In fact, I'm just telling this as a fact. For example, the most resolved, I'll put it this way, most rotationally resolved spectrum can contain, like your del mu as low as 10 to the power minus 12 centimeter inverse. Okay, right? So that is how accurate you can measure your data. All right. Okay, so I'll just sum up, like what we saw in this lecture today. We saw that the spectral lines, right? They're not just lines. There is some shape associated with them. In other words, they're going to have some finite width. There were three causes of the finite width. One was the natural width arising due to the Heisenberg's uncertainty principle. And there were going to be two more causes, which are one's due to pressure and due to the idea of Doppler broadening, okay, or a Doppler effect. Okay. Now, in this lecture, we only discussed the idea of width occurring due to the natural width occurring naturally due to quantum mechanical phenomena of Heisenberg uncertainty principle. Okay, right? And we saw that the Heisenberg uncertainty principle itself is nothing but a manifestation of wave-particle duality in nature, right? And when we use this particular expression, that is delta E times delta tau is greater than or equal to h bar by 2, we end up with a natural width. That is the width arising due to the quantum mechanical wave-particle dual nature of matter and light. Okay, right? So we did not see the derivation. We shall be, looking at the derivation in a tutorial. Okay, and we saw that, based on this formula, we can get the magnitude of the natural width of all these spectral lines. And given that electronic transitions are going to be much higher in energy than rotational and vibrational transitions, we understand that for vibrational and rotational transitions, the natural width is going to be much smaller. Okay, on that note, I end this lecture, and in the next lecture, it's perhaps time is also ripe for a tutorial. So what we shall do is we shall be discussing pressure and the Doppler broadening, and followed by that we shall be having a tutorial session. Okay, thank you so much.